Hello and welcome to the Daily Space. Today's episode may be a little bit rough around the corners. We had breaking news just as we got ready to go live, and I think you'll find it all exciting. So, this is the Daily Space for today, Friday, April 17th, 2020. I'm your host, Dr. Pamela, and I am here to put science in your brain. It is Friday. I don't know about any of you, but last night while I was trying to complete my timesheet, I determined that Tuesday was about 10 years ago. My brain is full and ready to sleep in tomorrow, and the news was conveniently easy on the mind to help us through this final day of the week. Not only do we have nice, pretty news, but we're also going to be joined by Dr. Emily Levesque. Emily Levesque, I can do this, people, an assistant professor at the University of Washington. She will be discussing her latest research into what may or may not have caused Betelgeuse to get so captivatingly dim in December and January. But before that, I want to let you know that astronomers study stars in lots of weird ways. And one of the most surprising ways, even to other astronomers sometimes, is us stellar astronomers, we defocus our images sometimes. Yes, folks, those of us who have tried to get the best possible measurements of stellar brightnesses in non-crowded fields. This only works when your starlight doesn't overlap. Those of us who've tried to get the best possible measurements of brightness in non-crowded fields will actually unfocus the starlight so it spreads out over more pixels. I've done this with our Alari variable stars using wide field cameras. Nobel Prize winner Adam Rees has done this with Hubble Space Telescope, looking at Cepheid variables. And now, the CHEOPS mission does it with everything it looks at, as it searches the sky for planets orbiting stars. Now, a few weeks ago, we showed you this early commissioning image of a star without any planets. They were just making sure their telescope worked. Today, we are happy to share that this telescope has observed the star HD 92296, a star known to be orbited by the planet Kelt 11b. And having observed the transient with a new level of resolution, they are able to more accurately measure things like the size of planets. And when fully operational, this mission will be able to see smaller worlds than we've previously been able to see. CHEOPS uses the planetary transit method to see where planets are located. This is the same technique used by Kepler and many other telescopes. You can even do this in your driveway if you have a good enough scope. And I don't mean big. You can do this with a 4-inch scope in your driveway. It's how accurate your camera is that matters. Now, as a planet passes in front of its home star, from our perspective here on Earth, it blocks more and more of the star's light until it is completely in front of the star. The time the planet takes to go from taking just a tiny bite out of the star's light to being fully in front of the star's disk varies based on how big the planet is, and how far from its star it happens to be located. By being able to accurately measure the light curve going from nothing but star to star with a planet in front, we are better able to understand what factors go into planets being dense little super Earths versus bloated out ice giants of very similar masses. And we can do lots of other things, but that's the research I personally am most interested to see. While CHEOPS is still in the checkout phase, everything is looking good, and the mission team hopes to transition into routine science operations at the end of the month. It is my hope that the next time I mention this mission, it will be to bring you news of, well, fabulous advances in our understanding of known worlds and discoveries of new worlds. Now, in every scientist's life, there are discoveries that radically change how we view, well, our entire universe. I still don't know what the biggest discovery of my lifetime will be, but I'm hoping that when I'm old and crotchety, I'll be joking about, well, how we had a 30-year mistake of thinking the universe was dark, had dark energy as its dominating constituent. Um, it's a hope. It's a hope. And I'm also hoping to take joy in a lifetime of seeing our understanding of solar systems grow and grow as we find them orbiting alien stars, and as we explore local worlds with our ever expanding fleet of robot collaborators. We have gone from the discovery of one planet being exciting to, I don't even generally cover news of new solar systems unless there's something particularly cool. But today I actually have a discovery that is just so silly that it needed to be covered. Using ground based SOFI spectrograph, astronomers from the University of Geneva have studied a 6-planet system orbiting the star HD 158259. Now, spectroscopes see planets by looking at how they tug their host star to and fro. And this is the Doppler shift method of finding planets. And the system they looked at includes one super Earth and 5 mini Neptunes, tightly packed together around a fairly average star. So it's a system. It's kind of cool, kind of boring. Now, what makes this particular system interesting is these stars are kind of in resonance all the way down. Um, yeah, they're doing their own version of rhythm and jazz, but it's more like how it's done by a middle school versus how it's done by a top end, well, drum corps. These worlds are in a pretty close to 3-to-2 ratio. This means that the inner planet goes around 3 times for when the next outer world goes around twice. The world out from that world goes around 3 times for every time that second planet goes around twice, and on, all the way out through all 6 planets. Imperfectly. Again, this is like a middle school drum section, not like a synced up professional gig. Still, it's kind of cool. And I got to say, it's partnered with one of the worst, best intentioned graphics of the year. This is why I waited to show it to you. Now, as someone who plays music, I look at this and I'm like, wait, but those planets in the triplet aren't evenly spaced. And why are they all basically, I do not understand. This hurts my brain, but it was so well intentioned. Folks, kudos for trying. I know what you meant. Distribute your planets more evenly next time. But again, it's more like a middle school than perfectly spaced. So maybe they got it right. Anyways, this is a really cool discovery. And it's fabulous in its just not quite rightness. For those of you who are just listening right now, we'll have this graphic over on dailyspace.org. Now, that's on this Friday, all the new news we have, but don't think of going anywhere. In just a moment, we will be joined by Dr. Emily Levesque, who will be discussing Betelgeuse with us. So please stand by. All good things will come after the break. Hello, everyone, and welcome back to this continuing episode of Daily Space. We are now joined by Emily Levesque. And Emily, about a week ago, you tweeted about Betelgeuse, and I was like, oh shit, I don't want to explain this. I'm just going to have you on because this is cool and awesome. Can you please tell people who you are and what it is you have been doing with our favorite star, Betelgeuse?
Yeah, so I'm a professor at the University of Washington, and my research specialty is red supergiants. So Betelgeuse is probably our most famous red supergiant and one of the closest red supergiants to Earth. So it started behaving very strangely about 6 months ago now, and I got too curious to stay away and wanted to do research on some of Betelgeuse's recent unusual behavior.
And this isn't like we all have pet stars we've been studying our entire life or wanting to be studying our entire life, but been thwarted by, if you're me, clouds. So this isn't your pet star. This is a more modern passion in your research.
Yeah. Um, they I've actually been working on red supergiants since about 2004. But I was working on them more generally, and Betelgeuse very much came up as a result of studying these stars as a whole. I think these stars are fascinating, period. And then Betelgeuse is kind of sparked my curiosity.
And And with Betelgeuse, what other than the fact that it radically got dimmer was the thing about it, or was that the thing about it that caught your attention?
So that was the thing about it. And this might be something that we can show people, just show them what happened to Betelgeuse. If you grab the third slide that I sent you, you can see what Betelgeuse did. It was varying by about maybe half a magnitude, less than that, varying in the way that many normal red supergiants do. And it had been doing that for quite a long time, and observers just monitored it to keep an eye on it. And around October of last year, it started.
Now, you bring to this study a context in how these kinds of stars typically behave. Can you describe this typical getting ready to end of life that we've seen by studying basically red giants all over the sky?
So there's a yes and a no answer to that.
Okay.
We have a pretty good sense of some of the strange things that red supergiants do. One interesting thing is that we know these stars pulsate. They'll actually kind of shrink and grow because we think of instabilities in the star's atmospheres and sort of outer layers. We also know that they have these big giant convection cells on their surface. And there's an amazing example of this on slide 5 if you bring that up and play the movie,
Yeah.
where the surface of Betelgeuse or any red supergiant will be comprised of these few big cells that basically work like the boiling bubbles that you see in a pot of water. Hot gas will get dragged up, and then it'll make the surface look a little hotter and brighter. And then that gas will fall back down, and the surface will look dimmer and cooler. And in a star like Betelgeuse, it makes it look like this wild amoeba boiling star creature thing. It's so cool.
It
Um,
looks like it's out of Star Trek.
it looks fake, and that is a simulation of what we think a red supergiant surface should look like. But if you go to the very next slide, you can actually see a picture that a group in Europe took of Betelgeuse using an amazing set of telescopes in Chile. And you can see those sort of bright and dark patches and mismatches that we think are coming from convective cells like that. So we know that there are normal things that will make a red supergiant's brightness change, but we also have a sense of the time scale of those things. Those pulsations take months to years, and those boiling cells at the surface take about a month to give us a visible change. What we don't know much about is what a star looks like right before it dies, as in the days or the months before they die. We know that a very massive star will fuse heavier and heavier elements in its core. At the very end of its life, it's fusing silicon for like half a day in its core. And we don't even think that the consequences of that have time to make their way out of the star and be visible at the surface before it dies. So we don't have great models on whether a star should get brighter, get dimmer, change color, do something very strange in those last cosmic moments, so days or weeks before it dies. So when Betelgeuse started behaving strangely, I think a lot of people picked up this idea of maybe the strange behavior means it's about to go supernova. And they weren't really citing scientific backing for why that was. I think they were just like, this star is the sort of star that could produce a supernova. This star is doing something weird.
Well,
Maybe this is what we can expect.
to be fair,
Yeah.
I know that you and I were both raised on the okay of the stars that you can see with your naked unaided eye, which ones are most likely to go supernova, and the answers are Eta Carina and Betelgeuse.
Oh, yeah. Mm-hmm.
And so we were raised on this. And
Mm-hmm.
given the state of the world we live in, even back in December, the idea that we might have happiness brought to us in the form of an exploding star that probably has no habitable worlds, we all hoped, even if we knew scientifically it was impossible.
Oh yeah, I had people asking me, "Do you think Betelgeuse will go supernova?" And my answer was always, "Almost certainly not," but leaving the question open. And it wasn't to be cute; it was because we truly maybe this was the sign of it going supernova. Odds were it was not, but we couldn't say for sure. And yeah, we were all rooting for it. It's so fun to imagine what it would be like here on Earth if we had a galactic supernova. So nothing that poses any danger, but something that gives us this just epic fireworks show in the night sky.
And we're able to get a sense of how long these different things happen, when they not when, we don't know the when, how often these things happen and how long they happen through our own ability to find them. Because if something lasts for a really long time, the odds
Mhm.
are we're probably going to see it doing that thing that it hangs out doing for a really long time. But just like you might not catch every time your cat decides to steal something off your desk because it's a little ninja thief, um, we don't always catch stars doing the fast paced little tiny transitionary things because it's too brief.
Right.
Now, we've seen at this point tens of thousands of supernova, but most of them are far away. How do we get the sense of, well, how long the different phases of these red giants are and just what it is that we should be looking for?
Right now, our best picture comes from what we call stellar evolution models. So we'll simulate the lifetime of a star from the moment that it's born, which means the moment that its core starts fusing hydrogen. And then in our models, we can speed up time and we just
Yeah.
hit play and watch what that star will do over 5 or 8 or 10 million years. That seems like a ridiculously long time, but a red supergiant dies after 10 million years, and a star like our sun is going to live 10 billion years with a B. So it does give us a sort of speedy look at a star's evolution like this, and we can look at how much of its life it spends as a red supergiant, where by this point in its life it's fusing helium in its core. We can look at what we think the surface is going to do, how the temperature might change, how the brightness might change, and guess how these stars are going to look as they reach the ends of their lives. And then we can compare those guesses with observations. We'll observe a whole bunch of red supergiants and see that they agree with our predictions of temperature and brightness and what we expect these stars to be doing at this point in their lifetimes. But we obviously haven't had the chance to watch one star change from a blue to a red supergiant because that takes such a long time.
And we do have cool little mile markers to put our models against, where we look at things like globular clusters. We look at things like dwarf spheroidal galaxies that don't have that many epochs of star formation, and we're like, okay, so we know how old the star system is. This is what our stars should look like at this point. This is what our stars should look like at this point. And so it's the analogy I like to use is it's like sitting in a shopping mall and looking at the people who pass by and trying to understand human growth and aging. You get snapshots and you just build the pieces between those snapshots.
Yeah, exactly.
Now, with a star like Betelgeuse, a lot of people have been able to say, hey, it probably has 100,000 years yet. How are we getting at proclamations like that?
It's an estimate of where we think it is in its life and how much time we think it has left. And there are big error bars on all of those guesses. We know that it's now a red supergiant, so it's fusing helium instead of hydrogen. And we know roughly how long helium fusion takes in a star like Betelgeuse. We've been able to estimate the mass of Betelgeuse, which tells us even better exactly how long we expect it's going to live. And we can make some guesses as to how long it has been in this evolutionary phase. But it's still very much a rough estimate. We can guess that it's probably fusing helium. It might actually now have moved into fusing carbon, but we don't have a really clear way to tell. And what we basically do is we sort of hit a road sign for, we know that the star has gotten at least this far in its evolution, so it's got about this much time left, and then make a guess based on how long that remaining time roughly is. Um, but it is really funny to see people talk about to explode and then putting it into astrophysical terms, because 100,000 years is a pretty short amount of time astronomically, but not for us. And it's
Yeah.
really funny to go back through old literature and see people writing things like, oh, we think we see signs that Betelgeuse is shrinking. That means it's going to explode any day now. And it's written in like 1962 or something like that.
You know, optimism runs eternal, and
Yeah.
I don't think there's an astronomer anywhere that doesn't want a star like Betelgeuse that we know isn't pointed directly at us with its rotational pole. That is a key. We don't want that. Um,
Yes.
we all want this booger to explode so that we can see it with our eyes during the day. And there's a lot of other really cool scientific things that we could learn when it goes boom, because we can observe its spectra and the details of the explosion and the nebula around it. But that's all for like generations from now. For us, we get to see how a star whose outer atmosphere makes the Earth's atmosphere look thin, how its outer atmosphere is changing. And we have a lot of ideas, and all those ideas got thrown on the table when the star got so dim. There was the dust idea, there was the convective cell idea. Can you go through all the different excuses we came up with for why Betelgeuse might be getting so faint?
Absolutely. There were really three main guesses for why it had suddenly dropped so dramatically in brightness. And the first was those sort of pulsations that I talked about. We know that Betelgeuse pulsates and will shrink and grow and shrink and grow. So we might have just hit a minimum that was a bit more dramatic than past minimums. I don't think a lot of people liked that as a sole explanation, but since this was a known reason for
Yeah,
why Betelgeuse varied, it made sense to point to it. Another idea was these convective cells. So the idea that maybe the surface of the star had just temporarily gotten unusually cool. When a star like this gets colder, it's emitting less light at the wavelengths that our eyes can see. And for a star like Betelgeuse, it actually is able to form molecules in its atmosphere that absorb light, again, right in the wavelengths that our eyes can see. So if the star's surface had temporarily cooled off because of those big convection cells, it would have made it look wildly dimmer. So that was a very popular explanation. And there were some people that kind of combined explanations one and two, that maybe Betelgeuse had these convective cells going on all the time, and Betelgeuse had these pulsations going on all the time, and we had hit an unlucky combination of the two that made
right.
Betelgeuse look especially dim. The third explanation, which I haven't mentioned yet because it is my favorite based on the research that we've done, is dust.
Yes.
We know that stars like Betelgeuse and other red supergiants will sort of periodically puff off dust. They'll shed mass from their outermost layers, and then that mass condenses in the interstellar medium and gives us these little tiny dust grains that can kind of sit in the way and absorb light.
Yes.
We even know that the kind of dust that red supergiants make is a little weird. A lot of dust in space preferentially absorbs blue light but lets red light through, so it just makes things look redder. We think that the kind of dust that these stars make is a little bigger, and it just makes everything look gray and dim. It's like having dust on your window. So that was the third explanation for what Betelgeuse could have done. It could have recently puffed off a bunch of mass that turned into dust and temporarily blocked Betelgeuse's light to make it appear dim.
Now, in passing, a lot of people went, but it could also be like a star spot, a giant star spot. And there's a lot of problems with the giant star spot theory. Can you just like push that one aside as no, real fast for us?
So I think when people imagine a star spot, they're imagining a phenomenon that's much more common in low mass stars. When I hear somebody say star spot in reference to a star like Betelgeuse, I immediately imagine that they just kind of mean the convective cells,
Right.
that they mean those big variations in temperature and brightness on the star's surface. I was very impressed that nobody brought up alien megastructure for
our
Betelgeuse, so
our
we
audience
left
is
that
our
happily.
audience is really good, really good.
Yeah.
um, all right, so we're down to basically convective cells and dust. And what observations are needed to try and differentiate these two possibilities?
The main difference between the two is that the convective cells would involve the star itself fundamentally getting colder, whereas the dust would involve the star's temperature really not changing much at all. We're just sort of blocking its life by putting a screen of dust in front of it. So, what we decided to do was take observations to measure Betelgeuse's temperature while it was really dim and compare it to its temperature. We happened to have some observations of it from back in 2004 when it was behaving perfectly normally. And the idea was that if we saw a much colder temperature in 2020, then that would lean toward convective cells and temperature effects as the explanation. And if the temperature hadn't changed very much, then it suggested we were likely seeing dust.
And in this case, just to repeat again, the dust is acting like a neutral density filter. It's
Exactly.
pretty much equally blocking all colors. It doesn't care. It's just dimming things.
Exactly. Yeah.
And I think I've got that wrong explained on this show before because I, like everyone else, thought the dust preferentially let red through.
Well,
Um,
some dust does. Red. Part of this reasoning is that we think red supergiants make an unusual type of dust. Dust will let red light through, but not blue light normally because the dust grains are really little.
right.
And we think the grains of dust formed around red supergiants are bigger. People have actually tried to measure the size of the dust grains, and they come out as something like 50 times larger than the dust we see in the interstellar medium. So that bigger size gives us that gray screen effect.
That is super cool. I had no idea. And if that's happening, and Betelgeuse doesn't totally leave behind all of its dust as it zips through the galaxy, there's going to be one heck of a supernova remnant when this thing goes boom.
The, it's going to be fascinating to see what it looks like if
N-
we get the chance.
If we get the chance, we probably won't unless we have robot bodies. My co host Fraser Kane believes firmly we will be around in robot bodies. Now, you guys took the observations, and what did you find? And what was the moment when you're staring at your screen and you finally get the calculations complete?
So I should explain what observations we took to get to that. So we took a spectrum of Betelgeuse, and it sounds like most of our sort of watchers and listeners know what that means. But
Yes.
just to reiterate, with the spectrum, we'll take the light from a star and kind of sort it according to wavelength. So we'll put the bluest light at one end of a plot and the reddest light at the other end of a plot, and then see what it looks like. And we were taking spectra to see if we could see any signs of those molecules in a red supergiant's atmosphere absorbing light. In a red supergiant's atmosphere, you get molecules of titanium oxide. And the colder the star is, the more titanium oxide you get. So you see these big absorption lines coming from those molecules. If you actually pull up slide number 4 that I sent you, that
Yep.
plays a little video animation, and you can see what a red supergiant spectrum looks like as it gets colder. The simulation goes from 4,000 Kelvin down to 3,400 Kelvin. You can play it and then arrow back and play it a few times so people can see it. You can see these sort of bites coming out of the spectrum as a star forms more and more titanium oxide molecules and absorbs more and more light. So what we were trying to do was get an observation of Betelgeuse and compare the depth of those titanium oxide lines in 2020 to the depths in 2004. And if the star was much colder, the lines would be much bigger. You can see what we found on slide number 7 that I sent you.
Okay.
The red spectrum shows Betelgeuse in 2004, and the black spectrum shows Betelgeuse in 2020. They're really not that different. There's teeny tiny differences. There's small variations. Betelgeuse looked a tiny bit cooler in 2020, but well within the normal range of variations for a typical red supergiant. It hadn't gotten nearly cold enough to explain what we'd seen. So we got this data on the night of February 14th. My collaborator, Phil Massey, was observing with the Lowell Observatory Discovery Channel telescope. The Lowell Discovery Telescope, I think, is now its new name. And he sent me the data pretty much as soon as he took it. And I was working on it on our, like, sitting at my coffee table.
And
And
just to explain to everyone out there, spectroscopy is not like photometry where you can sit at your computer and process it in real time and 30 seconds after you have the data know what your results are. Spectroscopy is a royal pain in the words I shouldn't say on Twitch because you have standard lamps, you have standard stars, you have to convert everything from your detector space, correcting for issues in the detector. How long per image does your pipeline take you?
so this Phil actually reduced the data pretty much in real time at the
Okay.
telescope. So I think it's very true that photometry takes much longer than a few minutes for most of us. But for someone like Phil, he was able to do the reductions almost immediately. And he did it using IRAF, which is
Yeah.
a data reduction package that he is an expert on. So he was,
IRAF is
yeah,
the most powerful software out there and the most effective way to make your graduate students cry.
it is its user interface takes some getting used to. I remember learning it and being really scared of the command line because I just learned Unix, and fortunately Phil was my teacher, so I now love it and find it
Yeah.
very useful and helpful. But it has a learning curve, especially if you want to use it effectively, for sure.
Yeah.
But Phil got and processed this data immediately and emailed it to me. And I was comparing our observations of Betelgeuse to old data on Betelgeuse and to models. And I saw immediately, like sitting on the floor at my coffee table, that the spectrum looked almost the same. And I was expecting it to look much colder. I was hoping that those convective cells would be a nice, convenient explanation. And we were just amazed at how little the star had changed. And then we started exploring the spectra in more detail and exploring what else we knew about Betelgeuse in more detail. And we started seeing signs that really the star was no colder, but it looked like it might have a bit more dust around it. And that was the tip off of, wow, it looks like dust really is the best explanation for this, and not those boiling cells that we had, I think a lot of us had thought of early on as the best explanation for what Betelgeuse was doing.
And this idea of plain old gray dust is just, it's so simplistic, it's so elegant, it's so annoying to diagnose.
It is. We had actually been studying that back when we first worked on red supergiant, so back in the mid 2000s, and we'd seen signs that this dust was big grain and gray and not normal compared to the interstellar medium. And we'd gotten used to seeing the signs of dust like that, but they're pretty subtle and strange. And since then, people have done a lot more work on dust around red supergiants. We've continued to learn really interesting things about why the stars behave this way. But it was interesting to see the telltale signs of it come up in our spectra when we'd been expecting to see just deeper titanium oxide lines in a colder temperature.
Now, one of the confusing points about dust as the explanation is this is a semi regular variable star, which means that it more or less brightens and dims with a periodic several hundred day period. And it was understood that if this was part of its pulsation period, it would begin to get brighter at the end of January, beginning of February.
Mm-hmm.
And it did that.
Yes.
How is it that dust can be the explanation, but it's still rebrightened as expected? Or is it just the convolution of the two led us into a land of confusion?
I think this is very much an open question, and I don't know what the right answer is for that. It's entirely possible that it was a convolution of the two events. We do know that dust production from stars like this is pretty sporadic. So the star could have puffed off a bunch of mass that condensed into dust, and then the dust would dissipate and the star would appear to brighten as a result. And the time scale on which that happens could be very similar to what we're seeing. This idea of a semi-regular variable, I've always loved the term semi-regular variable because it's kind of regular, but so there's certainly a little flex and a little push in exactly when you would expect those variations to happen. But if you look at how Betelgeuse is varied, it's really clear that it was sticking to the rough time scale that we expected. Now, when Betelgeuse is pulsating, it's possible that that pulsation could then interact with what's going on around the star and where the dust is, the temperature of the dust, the size of the dust. So the two could be connected, but we really need more. I mean, by now Betelgeuse has recovered, but we got as many observations as we could. And I know people are working to analyze Betelgeuse in a great deal of detail. And maybe we will get some explanations once we look at all the data together that explains the timing as well as the appearance of what Betelgeuse was doing.
And one of the cool things about watching this story evolve and not being an observational astronomer anymore is I didn't have a foot in the battle. I don't know if that's an analogy, but it's what I'm going to go with. Where I heard all these different astronomers being like, I got data with this telescope. I got data with this telescope. And everyone was on a race to process their information. And I remember back when I was an observational astronomer, there'd be plenty of nights I'd be out on the telescope and get a phone call of, "Hey, this object just did something weird. Could you grab me a few images?" Or because I was observing 20th magnitude objects on a not quite big enough telescope, I'd be waiting for complete twilight and grabbing images of other favorite objects that I wanted to study during that twilight. We all cheat when we have telescope time and try and squeeze out extra science beyond what we propose to do. Do we even have a sense yet of how many people gather data that can at some point hopefully get pooled into a master study?
I I don't know that we have a complete sense. I certainly remember seeing a lot of early announcements coming up pretty much on Twitter.
Oh,
People were
yeah.
sharing astronomers' telegram announcements of the early data on Betelgeuse dimming, and then people would put out variable amateur variable observations on Twitter. People were releasing these beautiful resolved images of Betelgeuse showing that it had gotten dimmer, but all on Twitter. And one thing that was important to Phil and I is that we wanted our results, since we were making this declaration that we thought we had explained this behavior that people had been trying to explain for a couple of months, we really wanted it to be peer reviewed and refereed and submitted
Yes.
to a journal. So we
Yes.
were working. I wrote the paper very, very fast
Yes.
after we had finished some very careful analysis. But I remember going through it going, how do you cite a tweet? Is there a, is there an accepted journal format for citing Twitter? Because in some cases that was where the information had been shared. I know
Private
that
communication doesn't quite correspond to public tweet.
thoroughly public communication. Um, but,
Yes.
and I've been hearing since then, there was another great, quick and recently refereed paper that came out on observations of Betelgeuse with Sophia. So I don't know how
Oh,
much you've talked about Sophia on this channel. Slide 13 shows what Sophia is, just because it's always an image worth enjoying. So
yeah. And
Sophia, yeah. Yeah,
there we
Sophia is
go.
an infrared telescope that operates out of the back of a specially modified 747. The plane is modified to fly up into the stratosphere, so well above 40,000 feet. And because of that, it's above 95% of the Earth's water vapor. And we can observe at mid infrared wavelengths that would normally be blocked from clouds and water vapor in our atmosphere. So I know that Sophia got some very quick observations of Betelgeuse with multiple instruments. And those mid infrared wavelengths are great instruments for really digging into what's going on with the dust. There was a wonderful refereed paper showing some of the results from Sophia, and I know they have more, and they're looking for folks who are interested in exploring it and working in this mid infrared regime to try and explain what Betelgeuse did. I don't recall whether Alma was able to get observations of Betelgeuse or not. I know people were scrambling to get as many observations as they could. And like you said, sometimes that means calling your friend
Yeah.
and saying, do you have 5 minutes during twilight? Sometimes you have to submit a proposal. And then unfortunately, by early to mid March, for one, Betelgeuse was really starting to brighten. So the dimmest point in its observations had kind of passed as an opportunity. And observatories unfortunately started closing. So now it is, if for a couple of reasons we can't really get more data, largely because this behavior has passed and also because observatories aren't operating at the moment, but we have a wealth of data from when this was happening that we can keep exploring.
And this is where we need to start thinking about reaching out to our friends in the private world. So I can imagine like Dustin Gibson at Oceanside Photo and Telescope would have no problems grabbing photometry with one of his 30 inchers.
Mm.
The iTelescope network, and these are all fully robotic systems, so no one's life is endangered if you simply ask the telescope to open.
Well,
And
now we are still getting beautiful, in many cases, amateur, but spectacular amateur photometric observations. The
yes,
difficulty comes in that, unfortunately, it's very difficult to do, say, amateur millimeter wavelength astronomy
yeah, no,
or
not there yet.
amateur high resolution spectroscopy
Yeah.
or amateur, we're going to put a telescope in a plane and fly it. I do not recommend an amateur approach to Sophia.
And and this
But
particular object was even annoying when it before the world started to close because Betelgeuse is bright even when it's being faint, it's bright.
yes.
And that means that we so the The good part is it's a fairly equatorial object, which means you can observe it from pretty much any of the big telescopes on the planet because it is visible from both the northern and southern hemisphere. That is
Mhm.
good. The bad problem is it's like it's going to blast apart the detectors on anything bigger than a few inches unless you basically block off most of the front end of your telescope, stick a bunch of neutral density filters in. We have ways,
Mhm.
but the only way not to blast a detector apart is actually spectroscopy. And this was one of the really frustrating things for me as a graduate student is I'd be on the 30-inch telescope doing wide field photometry of dwarf spheroidal galaxies at 20th magnitude, which meant the smallest amount of haze, and I was in the kitchen sadly shoving my face full of desserts. Whereas the planet hunters up on the 107-inch telescope were working at naked eye brightnesses you can see through clouds.
Mhm.
So, since this is a naked eye star, you can observe it through clouds when you're doing spectroscopy.
Yeah, well, I this is where the size of the telescopes as they compare to the instruments they have is interesting. So, you were describing observing it. That was at Texas, right? With the
Yeah,
107.
yeah,
Yeah. So that has a wonderful variety of telescopes of different sizes, but usually we don't bother putting cutting edge instruments on the tiniest telescopes.
right.
So even with spectroscopy, we have to get creative. Our observations were at the Lowell Discovery Telescope, and that's a 4.3-meter diameter mirror. So we had to put a 7.5 magnitude neutral density filter on the instrument just to get a spectrum because yes, Betelgeuse is so shockingly bright. But to me, it emphasizes the whole adventure emphasized a couple interesting things about observing. And one is that this nimbleness of being at the telescope ourselves or controlling the observing time ourselves and being able to toss this one star in at the beginning or end of an
Yeah.
observation can be amazing for science. And it emphasizes that we need a wide variety of different types of telescopes to do our work. We can't just do
Yes.
all science with a 10-meter telescope, and 10-meter telescopes are amazing and I love them. But there is a beautiful type of science you can do with a little 1-meter telescope with a good camera on the back. And we need this full variety of instruments available to us to keep discovering things.
Exactly. And I will say, I used a camera on the front at prime focus. So there's sometimes you can do great science with a 1 meter with the camera on the front.
Mhm.
Um, it really is mind boggling how, in order to understand the full diversity of what's in the sky, we need a full diversity of everything on the surface of the planet, which, of course, becomes a funding difficulty. It also means that there was this debate a number of years ago, the Rocky Kolb Simon White debate, where they talked about the difference in how we do observations, whether we should have more instruments like WMAP that are dedicated to solving single problems, the gravitational wave detectors, LIGO, the Future LISA mission. These are billion-dollar facilities that solve one field of science, and it's not like you get to point tonight, I'm going to look at this black hole and see what it decides to radiate. But at the other side of this, you have the individual telescopes that aren't even Q based, that there is an observer assigned this night, which means that they can be nimble. And well, if they discover either something cool's going on or by golly, there's a Starlink swarm about to swarm my object, they just change what they're doing.
Yeah. I It's the combination of both that really amazes me because
Yeah.
I think there's a place for the big, expensive, but amazingly ambitious missions that can solve one problem. Gravitational wave observatories absolutely
Yeah.
fascinate me, and the science they've done is stunning. I think it's some of the most beautiful engineering we've ever seen. I also love that I think it's happened multiple times where something's been designed thinking that it'll solve one problem, and then
Hmm.
boy, look at the other problems it discovers. So
Hubble.
tests, yeah, Hubble, exactly. The most exciting thing about getting new telescopes is that point where we realize what we didn't know we were asking, where we
Yes.
point Hubble at a blank patch of sky and get a deep field back. At the University of Washington, we're one of the founding partners of the Vera Rubin Observatory, so formerly known as LSST. And I can't wait until we turn that on and find the thing we didn't know we were looking for, and
Yeah.
discover a whole new corner of science that hadn't even existed yet. But I also wonder, once we do that, will we want 30-meter telescopes? Will we want 1-meter telescopes? Will we want both? Will we want something we don't even know we have yet? So it's why you need this diversity of resources.
And there's something wonderful about this mixed method of survey versus observer computed time. And
Mhm.
VLA has the Very Large Array out in New Mexico has actually done a really good balancing job of doing both. Because for the longest time, it was the only game in town for the kinds of radio astronomy that it does. And it would alternate between doing these magnificent surveys, NVSS first. I no longer remember what any of these acronyms stand for, and with these surveys, it would observe vast swaths of the sky in a consistent depth. It was able to see across this entire region things down to the same faintness and the same resolution. And then folks like me would pour through that with our software, looking for cool things in the radio to follow up in the optical. But then at the same time, you could say, hey, can I have this many hours to look at this one specific thing? And this mixed method has been key. Now, with the LSST, Vera Rubin Observatory, we're going to be in this unique position where for the first time, we're going to have a many meter telescope that's a survey instrument instead of a user directed, which means all these things that just because these telescopes generally see such a small swath of the sky, we're going to see for the first time because they're
Mhm.
rare and you don't know where to look when you don't know what there is to find.
Yeah.
So we have strayed far, far afield,
Yeah.
but I think in good and interesting ways. Now that Betelgeuse is sadly mostly behind us, and we're not in a position to do like in the perfect world, I would love to convene this summer a workshop where come with your data. Let's see what we can publish in a week of everyone in one facility. We can't do that right now. Maybe we can do it on Zoom. That seems awkward. Um, so what are you going to move on and do next as we all figure out how to keep the world sciencing?
So I have a research group right now with multiple folks working on answering interesting questions about red supergiants.
Uh-huh.
So one of the graduate students in my group, Trevor Dorn Wallenstein, is looking at how things like binary evolution and rotation and things like that affect what happens to evolved massive stars as they start ending their lives. And you can actually see signs of things like binary evolution or rotation on what an entire population of stars looks like. He's also doing a lot of really cool work with variability in these stars and trying to use that variability to suss out what's happening to these, like what types of stars these are and what's happening to them. Another graduate student working with me, Catherine Nugent, is looking specifically at binary red supergiants and studying how many of these stars have binary companions, how many are interacting with their companions, who those companions are. So it's really just trying to dig into untangling many of the outstanding questions we have about how red supergiants work, about the types of supernovae that they make, about what these stars look like before they become red supergiants. I mean, that was something that Betelgeuse really emphasized to me, is just how many questions we still have to answer, and that we can answer with big sets of data or other red supergiants or other studies or models of massive stars that will ultimately become really useful the next time a single star does something weird.
And what's so cool about any kind of variable star is
Mm-hmm.
because these objects don't sit still,
Mm-hmm.
people have been noticing them for over 100 years. So for these visible ones, and there's a whole lot of visible semi-regular pulsating stars out there, because they're super bright, you can see them to large distances. So even though they're fairly rare, you can see them across such a large volume of space. We see a bunch.
Yeah.
And this means that it's not just a case of getting your own data today. It's also that fun library search, realizing, oh, wow, someone at David Dunlap Observatory looked at this in the 1800s. And it is always someone at David Dunlap Observatory who looked at it in the 1800s. Um, it sounds like you have some really cool stuff going. And if there's any one thing that you could tell people about these giant red stars, what is the one thing you would want everyone to know?
I would love people to understand just how cool they are. And this is not meant as a pun. They're very cold stars,
Yes.
but there are so many mysteries about these stars and so many details that we're just beginning to understand. This was one of the fundamental things that got me interested in stars. Is you think of stars sometimes as the kind of well understood little balls of gas on their way to becoming black holes or supernovae. And those little balls of gas are so poorly understood in some ways and have so many mysteries, and understanding what rotation does to them, what binary evolution does to them, what happens if you add a magnetic field, how they make that dust, what the dust does to the stars. These are all such fundamental questions, and they're about stars. They're about the
Yeah.
building blocks for galaxies. They're about the places where we make star stuff, what we're all made of. So there's so many mysteries to explore if you just take one star like Betelgeuse and then start poking it and start digging into it. And being able to do that on a universe scale is just the best job.
And this really brings home how much our field is uncovering the unknown unknowns. Back in 1998 when I finished my master's thesis, because I am old, um I was told, stop studying pulsating variable stars. They are a solved problem. And and so I went out and took good advice, I thought, and studied galaxy clusters.
Mhm.
But over the years, especially with Kepler initially, we keep having these punctuated moments of, oh, wait, we don't understand these at all.
Mhm.
And I love that the more we look at the universe, the more it tells us you silly humans think you understand things and you don't. And this is why we do science. It's to keep finding these answers that just lead to more questions, and it's awesome.
Yeah.
So where can people go to follow more about what you and everyone on your team is doing to help us understand these bright red stars in the sky?
So there's a couple places. My website emlevesque.com is a good place to go look for things like what our research group is up to. We'll put updates on new papers. I actually wrote a sort of professional astronomy text on red supergiants. It's called the astrophysics of, hang on, haha, it's called the astrophysics of red supergiants, and it's distributed as a free ebook. So if you have a university library subscription or similar, you can go read more about stars like Betelgeuse. I also saw several people in the chat asking questions about sort of the excitement and art of observing. So how we get observing time, what it's like to work at a telescope, what it's like to try and change plans at a telescope at the last minute. And I've actually got a popular science book coming out this August called The Last Stargazers, that's all about sort of the behind the scenes look at how we do astronomy and how we observe. So it tells stories of how we get access to telescopes, how we get to these telescopes in the middle of nowhere, and how technology and the advent of new observatories is changing the way that professional astronomers do our jobs. So if people are interested in that, it comes out August 4th and it is available for pre-order on Amazon, and it gives you a nice look at sort of what life as a professional astronomer is like. I unfortunately don't seem to be able to hear you anymore.
Oh, I'm sorry. I muted
Yeah.
because dog explosion upstairs.
Oh,
Thank you so much. Sorry, I was just saying this has really been a pleasure. Thank you so much for coming on with us today. And we're gonna have to have you back when your book comes out in August.
oh,
Um,
that'd be great. And I love talking about red supergiants and Betelgeuse. So thank you very much for having me.
oh, I'll talk variable stars all day long. My heart belongs to the RLRs, but really, there's a Keats quote that he only wanted a love as constant as a star, and if only he knew more about stars, if only he knew.
The volatility of star. I love it. Well, thank you so much.
So I am going to transition into ending out this episode. Thank you for being here, Emily. Like I said, we're gonna have you back, and it's really been a pleasure.
Thank you.
Bye-bye.
Bye.
So, and thank you, all of you out there in the audience, for staying with us through this amazing interview with Emily Levesque. I love variable stars. What can I say? Well, that's what I can say. I love variable stars. So today's episode of The Daily Space was brought to you, I'm your host, Dr. Pamela Gay, and I wrote today's episode, and I'm so pleased that we were joined by our amazing guest, Emily Levesque. This episode will be produced by Susie Murph, and we are a product of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our universe and beyond. Our episodes go out live on twitch.tv/CosmoQuestX. And if you're watching this over on YouTube, well, we invite you to join us any Monday through Friday at 1 p.m. Eastern. That is 10 a.m. Pacific. We are here thanks to the generous contributions of people like you. Your bits, your subs, your patronage at patreon.com are what allow us to do all the things we do. And we understand in these times that you may not have anything to give. Well, that's actually probably a lie, because you have you. Come join us. Hang out with us on Discord. Join us in, figuring out how to advance our understanding of the universe through our various software, citizen science, and science communications activities. And just join us in a game of Ticket to Ride, because for whatever reason, our community is addicted to Ticket to Ride. You're always welcome to join us, and you can find links to everything at cosmoquest.org. And I think that pretty much rounds out everything I have got for today. I would like to take any suggestions you have on who we should raid, and we will raid our stream over. This is me looking to see what all is going on out in the Twitter sphere. Timber Anew, that is an excellent suggestion. So everyone give Timber Anew a happy rocket welcome. And wherever you are in the world, have a fabulous morning, evening, or afternoon. And wash your hands. I'm off air. Thank you so much, Emily. We try and keep things. I need to be entirely honest. I invite on people whose research that I really want to hear about, and where I really don't want to do